Is that better? Okay.
Yeah.
Okay, then I'm not using the webcam now. Okay. That's a little bit weird because I won't be looking at this angle. So sorry about that. Yeah, that's unexpected, but hopefully let's come around with that. So this talk, I think, is not actually chromatic, but it's more a presentation of something in topology 3. It's about spectra and some like basic settings, and some of them you already seen in yesterday's house talk. But I'm going to probably rephrase it again. And the reference I'm using is basically Carey's note on stable homotopy category. And because I'm not using the same device, I can't copy and paste. Sorry. And previous years, people also gave talks on similar stuff, and I've been taking good use of that. I'm also be okay with recording posted, and after the talk, I'll try to send the notes to the organizers so you can access the notes online. But it's probably a version with more words, so yeah, it's harder for me to write a lot of things during the talk. But yeah, also, I think I have Asperger's, but some of the time what I'm talking doesn't make sense, but I try to talk slow and make it clear. Anyway, let's get started.
I'm sorry to interrupt. Can you say the reference again?
It's Carey's note, Carey Malkovich notes, the stable homotopy category.
Okay, thank you.
All right. So let's start with the motivation. And well, we know we have this spanner wet height category that is coming from we stabilize the space. So let's write out the objects. It's pointed CW complex. And then the morphism, because we have the Freudenthal suspension theorem, so the morphism is well defined because it's stabilized. Defined to be, we take the colimit of the suspension. Okay, so, but this is like only going to the positive direction, namely all the thing you get is connective. You don't have negative homotopy on this side, but we can also consider the part which has negative. So we can make the object to be the pair where you keep the x, which is the pointed CW complex, and add another component where it is the integer. And then the morphism between the pair is almost the same. It's again the colimit of the homotopy class where you have this modification of the integer, so things are allowed to be negative. All right, so what you get from here, this is already a triangulated category, and what it means to be triangulated probably is going to introduce in later talk. So in the word of introduction, it's very coarse and not precise. It's somewhere you have the suspension as a shift and you have the notion of co-fiber sequence. Anyway, but this category doesn't satisfy something we want. For instance, it does not preserve co-product. And that's bad because that means the Brown representability not always hold. Okay, so, well, this category apparently is not good enough. And we want to find a good category, and let's move on and see what we can approach that good category. All right, so as we already seen, let's do a recall that the spectrum has the following data. So first you have a sequence of space, based space. And then, okay, sequence. And you have a structure map. Sigma n is from the suspension of En to the next level. And by putting various of conditions on this En and the structure map sigma n, we can obtain special spectra as a subset of the collection of the spectrum. And we have also seen a couple of them yesterday already. So let's talk about that again. So first, if your structure map is an isomorphism or identity, then it's the only information of the spectrum is the space, and then you just do suspension. So it is a suspension spectrum. And the famous example is our sphere spectrum. And the next one is more close to the CW thing. It's the CW subcategory. I'll put category in quotation mark because we haven't talked about it as a category structure yet. So for that, you want to restrict the En to be CW complex. And you want the structure map also be restricted to the inclusions of subcomplex. And then you get the family of CW spectrum. And then another thing that often people talk about infinite loop space. And then for that, you want to consider not the structure map, but the induced map from the structure map, because we have the suspension loop adjunction. So what do we want to write down here? So the map induced from the structure map sigma n, but it is from En to loop En plus 1. So this, let's say, corresponding to sigma n. So this is an isomorphism. For every n, then you get the omega spectrum. Okay, so those are three families that are very important. But well, from previous talk, we know why we cared about spectra, because first, Brown representability, so it represents cohomology theory. Okay, so let me briefly write down the Brown representability theorem again. Okay, so let's start with a reduced generalized cohomology theory. And then we can find an omega spectrum such that, well, if we plug in N for the grading and plug in X into the theory, and then we get this homotopy class of mapping space for each N. And an example of that, well, I'll give 3 examples instead of 1. So if your cohomology theory is ordinary cohomology group with coefficients as abelian group A, then the spectrum you get is the Edinburgh-MacLean spectrum. And then if your cohomology theory, it is awkward to write down because often we also write KU there. And then it's corresponding to the spectrum, we write KU also, I think. So, and the same for MU. Okay, so we can see that there are strong connections between cohomology theories and the spectra. But in this, so far, our notion of spectra is not one-to-one correspondence. The spectra has more in the sense, if you have a map of spectra that is like not 0, but it could be like 0 in the cohomology theory or pass to the other side. But it's still strong connection already. So for cohomology, we have some kind of product structure, as you can already see in the down corner here, like cup product, etc. And we may expect that to also show up in spectra. So let's talk about that. All right, so let me just write down what I already mentioned. For the ordinary cohomology group, you have cup product. And for KU, we constructed by using the Grothendieck construction. Not the one I'm going to talk about in the next talk, is the additive inverse, that one. We construct that by doing the G construction of vector bundles, but it has an induced multiplication. It has an induced multiplication from the tensor of vector bundle. And then for the complex cobordism, you have the Cartesian product of manifolds. So those are all make them into multiplicative cohomology theory. And let me say one more word about the structure of the mapping space. So usually, if you have something like this, the structure on the mapping space is heavily rely on the target space, because you can just send it to the target and do multiplication there. So when we expect the multiplication structure on the theory will transfer to the target space as well. And then, well, in the ordinary case, we have Queen's theorem that is basically saying in good situation, we can identify the cohomology of a product with the tensor product of cohomology. So let me just write down the general case. I'll need to write down in good case. So in good case, you can pull out the smash product inside and it becomes a tensor. And then, well, if we pass it through the Brown representability, let me just use x and both x to write out the example, because it's easier to illustrate in that case. And then for the first one, you can use something like the diagonal. If the second one you're using y, then you probably need some kind of duality argument, but we are not coming into there in this talk. All right, and then you apply this multiplication to get something in the n plus m level. So in short word, we want a product on spectra. Well, okay, so I don't actually know historically, like why is this smash product coming out, like how the name is coming out. I think it's because it's stabilized of space, and in space we do smash product, and then for spectra we also do smash product. That's probably why the name is coming up, but I don't know. If you know that, you're welcome to share that with me. Anyway, but we call it smash product. So for space, well, the smash product is defined to be the Cartesian quotient out the one-point union wedge. And then we also define the smash product between space and the spectrum. That is, you just smash with the space for every level. But okay, so what's the abstraction if we want to define the smash product between spectrum? Well, I draw the diagram because I'm lazy. The problem is when you choose one level, let's assume we have like the nth level, and we want to define the structure map. So we want to go to the next level. I think the grading is probably not lining up, but yeah, bear me with that. So if we are standing in this spot and we want to go next, you can either go horizontally and add 1, or you can go vertically, add 1, but there's no way tell you where to go. And or you can say this suspension, you do not know like how to distribute that. So that's a problem, and this obstruction like maybe a more detailed version is well explained in Adam's blue book. I think the blue book is called Stable Homotopy and Generalized Cohomology. Yeah, I highly recommend reading that story, even though he is not giving a good answer in that book, but it's fun to read. Okay, so I'm not gonna review the secret yet. Okay, but we want a good smash product to the category of spectra to make it good. And what do we mean by good? Well, here are several axioms that we want the category together with the smash product to satisfy. And let's take a look at them. So first, well, of course, we want it to be symmetric monoidal, and what symmetric monoidal means will be fully explained in later, I think, Fuling's talk. But in general, we just want multiplication that satisfy associativity. So we have the square and the unit, so we have two triangle. And if symmetric, you want another triangle where you put twist there. Okay, so that's how the first one is coming from. And the second one, we want to keep the adjunction between from our top base space and the spectrum, that's the loop infinity and the suspension infinity. And we also want them to keep the multiplicative structure. So that's why it says it's a lax monoidal adjunction. Okay. And the third one, of course, we want the sphere spectrum to be the unit. And the fourth one is kind of explained from the second one, like what lax monoidal is actually mean. And the fifth one is, so we have this stabilization functor defined to be the colimit of loop n suspension n. And we want to identify that with the infinite version of that. Sorry, could you repeat that? Or say it louder? I cannot hear you.
Yeah, I think it misspoke, so maybe you can continue.
Oh, okay. Yeah, if you have questions, feel free to interrupt me because it's harder for me to see the chat. Oh, I see the notice posted. Okay. Yes, that is the notes I highly recommend. I read that for at least 30 times, I think. Anyway, yeah, so we want to identify the stabilization functor with the unit of this adjunction. That is, we go from this direction and come back. All right. And well, you can guess and type in the chat, can we find a category satisfy those 1, 2, 3, 4, 5? And well, the answer is nope. So yeah, sorry. If there's copyright issue with a picture, I'm okay to take it down. But, yeah. So this is actually Lewis' theorem. And it's explicitly saying there's no notion of category of spectra satisfy the axiom A1 through A5. And the paper, like Lewis' paper name is there a convenient notion of spectra? That's a very well written paper, and yeah. Okay, so let's briefly explain why. Okay, so first, well, we are assuming we have such category and we call the category spectrum. And we assume it satisfies all the axioms we can find. And because our sphere spectrum is a unit, it is a commutative monoid in our category. And because our loop infinity as part of the junction is a Lax symmetric monoidal functor, so we apply that to the sphere spectrum is also a commutative monoid. So, well, let's write it in another way. So this is loop infinity, suspension infinity of S0, zero sphere. And by axiom 5, we identify that with the stabilization. So that means the stabilization of S0 is a commutative monoid. So far, so good. Okay, but we have another theorem. That Moore's theorem says, well, there's not that many things that have the strict ring structure in this category. So it says, if our spectrum is a category, satisfies the axiom from A1 to A4, then if you have a strict ring spectrum, namely you have the multiplication is strict, then it can only okay, there's one more sentence, sorry. Then loop infinity of that spectrum is a product of Eilenberg-MacLane space. Sorry, for those you can hear dog barks, I'm sorry about that. Okay. Yeah, so it's a product of Eilenberg-MacLane space. Well, okay, so from this, our conclusion is the stabilization of S0 is a product of Eilenberg-MacLane space. But this is not true. Okay. Let me try to check for questions. Yeah, Q is a stabilization functor defined as the colimit of this. Other questions? Oh, I see there's some lag in the screen sharing. It should be okay. Okay, so let's move on. Well, we know that there's no way we can have a good category of spectra, but we can still have something. So let's see what people do. Okay, so here are some different approach to get a category of spectra. And let me add, so S module, this is by Emmendorf, Cruz, Mendel, May, so short as EKMM. And then later, Mendel, May, Schwed, Shipley have this notion of orthogonal spectra. Also, this picture I steal it from Carey's notes, so credit for him. And then later, Hovey, Shipley, and Smith have this notion of symmetric spectra. And so here there are a lot of details to talk about, and which makes this talk going forever. But yeah, that's probably not good. So I will briefly give some idea for each, but not going to say a lot of details. So let's start with the S module, that one. So the idea is they take use of the linear isometry operator to make things coordinate free, so it doesn't matter where to go if you still remember the abstraction for this defining the smash product. And for more background on Alpharad, I think the higher algebra talk is going to talk about that, but I'm not sure. Yeah. Anyway, Alpharad, in short, is a structure encodes how you multiply things. Anyway, because they want to use that, so they change the index from integer to the finite dimension inner product vector space. So it's essentially still integer, but it's more useful, so we can take the linear isometry operator on that. So we fix a universe that is R infinity. So and then we make the spectrum has gradients. It's also called pre-spectra in their picture, in their paper, sorry. So it's index over finite dimensional inner product vector space. And then also the structure map is index over two vector spaces. So you have the suspension of the difference of their dimension. Okay, so if this structure map is a homeomorphism for all of the inner product vector space, then the spectrum is called the Lewis-May-Sternberger spectrum. All right, so let's try to see how they construct the smash product. Well, ideally, you want to have something like that. So, am I making sense of? Right. So ideally, you want to separate like V and V prime, and then define it to be the smash product between E and F. So I should make a note. Yeah. But this depends on a choice. This alpha is a map from the direct sum of your universe, 2 copy of that back to you. So it is sending well, we don't want things to depend on a choice. So how? Well, here, let me briefly introduce the linear isometry of red. So the linear isometry of red, the nth level, it is defined to be the linear maps from n copy of the universe to U. And then there's one good thing about that, that is every level is contractible. So yeah, we have a lot of choice is okay because the choice is like all homotopic to a point. So so that means we can like sum up all the choices of the thing we do product. So they construct this thing called a twisted half smash product. And the notation is like this. And then, well, if you construct this product is not associative and it's not unital, and you need to fix that. And the modified term is the choice of L1 cross L1, where L1 is like the first level of linear isometry. So you also need to quotient out that. And then things are good enough for you to define a good product. And then, okay, I have just done the associativity. And for unital, you also need to restrict to all the spectrum such that, not such that, with if you smash with a sphere is isomorphic to itself. And then this kind of spectrum is called S modules. Yeah, so the construction of the EKMM approach is highly non-trivial. And I have definitely left out a lot of details and say things incorrectly sometimes. But this is, I think, fit in the storyline and kind of give you the idea of how they do that. If you're interested in that approach, please go to read their paper. Okay, so and then we have the symmetric spectra approach. The good thing about that is you can write out an explicit formula for the smash product, which I'm being lazy and have it pre-written. And but let me put the setup first. So the symmetric spectra, it is equivariant space as a sequence of its component. Sorry, I might say things not making sense. Anyway, so E has every level is pointed space and is sigma n equivariant. So this is a symmetric group. It has an action of symmetric group and play well with the structure map such that the composition I should write the composition. Or maybe not. Okay. This composition where you put one copy of the sphere once a time, and then keep going until you hit the P plus Q level. So this composition, you want it to be sigma P cross sigma Q equivariant. Okay, so that's their construction, and the smash product is explicit formula is defined in this way. So you want to wedge all the copies of PQ that add up to n. It's kind of adding the diagonal line of one grading. And then you also want to identify here you have the P copy of sphere, and you can either smash it into the F component, or you can smash it into the E component, and you want to identify them. And how the map goes is in this light blue color. So yeah, the formula is slightly tedious, but at least we have a formula, and that's a lot of progress. Also, this formula is much easier from the EKMM approach. Okay, so I am gonna take a shortcut for orthogonal spectra because it's almost the same, and Carrie said the same thing. Sorry. Yeah. So if you replace the sigma n equivariant with On, where On is the nth orthogonal group equivariant, then everything follows and you can get the orthogonal spectra. But the most modern way to understand orthogonal spectra is you construct an orthogonal category and think of orthogonal spectra as a functor map out of that category. But yeah, I think I might not going to go there based on the time restrictions. Oh, I see some no more questions. Okay. Okay, so we talk about those three candidates. Let's do a comparison about pros and cons. Yeah, also, by the way, they all fail the last axiom. That is, the stabilization functor is not the same as the unit that is like loop infinity, suspension infinity of that. Okay, so we first have EKMM, and we say S module for that one. And then we have the symmetric spectrum, and we have the orthogonal spectrum. Sorry, I'm doing Steiner square too much. Okay, so the good thing about S module is, well, the loop infinity will give you strictly to the zero space information. And then all the objects are vibrant. And then you also have the stable homotopy equivalence is the weak equivalence. Of the model structure if we put down there. And the cons is, well, we already seen that it is really hard to define this mesh product. Okay, so for the symmetric spectra, there's convenient model structure to put on the commutative ring. And it is easier to generalize to simplicial sets because we know space is almost simplicial sets. So if you want to do things with simplicial sets instead of space, then symmetric, this definition makes a lot more sense. And then, well, it also have cons that, well, the stable homotopy equivalence is not the weak equivalence there. Because if you take the, well, you take the stable homotopy, I'm kind of saying the same thing again. If you take the colimit, it's not gonna match with the right notion in that category. So you probably want a weaker notion than that to be the weak equivalence there. But that's like a huge drawback, actually, because, well, this is the most natural thing we expect to be the weak equivalence. And for the orthogonal one, first, it is easy to generalize to equivariant context. And we know Hill, Hopkins, Ravenel did that, and that's their HHR paper. Is equivariantize a word? I don't actually know. Okay. Anyway, so all objects are also vibrant, and stable homotopy equivalence is weak equivalence. Okay. So often when we mention spectrum, we are not thinking of like the actual, those three model of spectra. We are thinking of the stable homotopy category, and it is the homotopy category of those three. So yes, they share the same homotopy category. Let me write it down. And how to get the homotopy category? You invert the weak equivalence. I do not have a better way of saying this in a short amount of time. So, but you do need to be careful. So let me just briefly talk about that. So this two is already a closed symmetric monoidal category under the smash products formula given above. So yeah, you can talk about monoids there. And well, but often, well, let me just say the product first before I actually say things about ring structure. Okay, so you can get the smash product in either of them and get the derived smash product on the homotopy category. I think for the homotopy category is also called the derived category, and you can see that in future Hannah's talk, I think. So let me put smash L there, where you define this as so the C is the cofibrant replacement factor. Okay, so the sphere spectrum is cofibrant, so it is also the unit in the stable homotopy category. Let me give it a name, so stable homotopy category. Yeah. So this category has good property, it is triangulated. And of course, it's stable from the name. And what is good about stable? Well, the fiber sequence is the same as cofiber sequence at least, and that's already very good. Okay, so I have 6 minutes to talk about ring spectra. That's good. Well, okay, so from the name ring spectra, you may think, oh, okay, so that's so spectra has a ring structure. Yes, sometimes. But no, actually, this notion of ring spectra, I think it's because people also call the object in the stable homotopy category as spectrum. And what it means to be a spectrum is really not clear, and you need to tell from the context. So the notion of ring spectra is more like an H space, but I don't know if there's a notion of H spectra. But let me just write that is like H space. So formally saying it is a monoid in the stable homotopy category. Or you can think of that as an actual spectrum with a multiplication and a unit commute up to homotopy. Okay, but often, well, that's a little bit boring because you only have like the square and triangles and the commute up to homotopy. And well, we can talk about richer ring structure. And that is not enough, and we need to take good use of the operad to encode that. And I have some questions that is fun, and you can put the answers in the chat if you want. So what thing you exchange during weddings and commute? Well, I'll answer that. That is a commutative ring, of course. And more version. So what thing you exchange during weddings and almost commute? Well, then that will be an E-infinity ring. Okay, so this E-infinity ring is, let me think of how to make my word make sense. Yeah, so this E-infinity means highly commutative, and you have all the things commutative up to homotopy. And if you have things that are E-infinity, is guaranteed to be a ring spectrum. That is okay. I'll write this. So if E is an E-infinity ring spectrum, that implies E is a ring spectrum. And well, not vice versa. And actually it is confusing because you can also talk about the nth stage of E-infinity. But let me give some example at almost the end of my talk. So the ring spectrum example, well, the Mu and Ku, they're all ring spectrum, and actually they're also all E-infinity ring spectrum as well, and sphere also. And I only know one example, and I don't know if we have talked about, probably not, in the talks regarding to the complex cobordism. But I'll just briefly say that because I think that's fun. So we may know that Mu splits as the wedge of Brown-Peterson spectrum, but this BP is not E-infinity. I think it's B4 or something. So it fails to be an E-infinity ring spectrum. Okay, so I think that is all I have for the first talk. Thank you.